Okay. I want to introduce time reversal symmetry. So this is slightly more advanced, but I think it's not terrible, and there is no section like this in the book. But if you look at the problems 636 and 637, you are going to find almost everything I taught today. I just tried to make it like more like a lecture material. So first, I need to tell you what time reversal symmetry is. So this time reversal is like a misnomer. So like almost everything else in physics, we should never rely on what people call things. Right? Things are called whatever they are called, and they generally do not help. Maybe if you want to motivate, you can think about this as like motion reversal. Okay? And the basic idea is like you have some path, right? The particle is going through some path, and suppose this is like at t is equal to 0, and I have, suppose, some momentum p, and what we mean by time reversal is like right at that point we reverse p like this, minus p, and let the system evolve. So that's the operation, what we mean. That's why I want to call it more like a motion reversal. So therefore, we think about this as v or p goes to minus v, whereas, let me actually use p. This is at least what we motivate with, p, and we also still think r to be r. So that's what we mean, at least classically. And if you think about Newton's laws, so F is equal to ma, this is equal to m d squared r d t squared, and here F is equal to some force gradient of some scalar potential. Then from here we immediately see if you can solve this, right? This is like a second order differential equation. If you can solve this for x of t, and wherever you substitute x of minus t, this is also a solution. Is also a solution, because there's t squared. If you put, wherever you see t, you put minus t, you are going to obtain a solution for this, which is exactly the same. And you should compare this. Suppose you add dissipation or friction, something like minus m v over tau. That's typically what we have for dissipation. This breaks this symmetry. So this is not the case anymore. X of t is not, x of minus t is not a solution anymore. Good. And we can also think about a very common example is like particle in a magnetic field. Suppose we have like this magnetic field out of page, and with right hand rule, if I have this v, right, a particle is going to circulate like this, and it's, I don't know, momentum is something like this, and at exactly this moment, if I reverse p like this, right, and keep magnetic field unchanged, what is going to happen is like this path is going to turn in the other way. So this is clockwise, this is counterclockwise, and in that case we say that time reversal symmetry is broken. So if b is constant, that's what we mean by background field, background b, then time reversal is broken. There is no time reversal symmetry in the sense I outlined here. So this is minus p. Of course, if we are going to reverse the motion of everything, we are also going to, if you insist that the motion of the particles who is generating B should also be reversed, then B will be reversed and there will be, right, no change, and the motion will be time reversal invariant. So you have to make sure which one you mean. Typically, we take B to be background field and then think about time reversal with the fixed background. But if you are like a fundamental physics and particle theory and things like that, this B is also a dynamical field and it can also change with this operation. Good. So we can also think about, let's think about gauge fields in general. So gauge fields E and B. And of course, we deduce their behavior under symmetry operations from their equation of motion, which is Maxwell equations. We have del dot E is equal to rho. There is epsilon 0, or depending on the choice, there's like 4 pi here, but I'm not going to write those. Del dot B is 0. Del cross E is equal to minus del B del T. And the last one is del cross B. Del cross B is equal to, there's again some constant I'm not going to write, so this is J plus del E del T. Good. Now let's start from here if you want. You can take, with this motion reversal, right, you can reverse the motion, but this does not change, no change. So nabla is nabla with the motion reversal or time. If you want, this is sometimes misleading and we have to be careful, but you can think about this like t goes to minus t. Okay, let me put it in quotation mark. That means we need to be careful. And if t goes to minus t, nabla doesn't change. Therefore, if left hand side doesn't change, right hand side should not change. We require from here E with time reversal goes to E, okay, because rho goes to rho. If I look at here, right, so this one is like some rho times V, and it's going to go to minus J with time reversal. I'm going to reverse motion. And there is like E here which doesn't change, but there is T, so this goes to minus del E del T. Nabla doesn't change. For this to work out, B should go to minus B. Okay? So this doesn't give any new condition. So in summary, what we require is rho should, with time reversal, go to rho. The current density should go to minus current density. These are like sensible. But also, E should go to E, and B should go to minus B. So compare this with parity, right? In the case of parity, what we said is like E goes to minus E, whereas B goes to B. Good. Any questions? So far, we are just setting up the terminology. So this was classical mechanics and classical electrodynamics. Now let's come back to quantum mechanics, and our starting point is always Schrödinger equation. And this is I, h bar, del psi, del t is equal to minus h bar squared over 2m plus v psi. Now suppose, so you solve this equation and you found a solution, like say psi of x comma t is a solution. Now can we find another solution by just using this solution? So the way we do it is like in 2 steps. So number 1, I'm going to take the complex conjugate of this equation. So if I take the complex conjugate, I'm going to have minus here, complex conjugate here, and complex conjugate here. Actually, let me also put the arguments. So this is xt, so this is xt. And in the second step, I want to change. So this was the complex conjugation. I want to change wherever I see t, I want to put minus t. Okay. So I put here minus t, here minus t, and here minus t. And there is nowhere else. And now I can combine this minus and this minus, right? And I can erase this one, and I can make this one t. And now I see this equation, right? And this equation are exactly the same, whereas the solution in the first case is psi of x comma t. In the second case, my solution is psi star of x comma minus t, right? If you give me a solution, by this operation I immediately obtain another solution. Good. So this is the key move, and this is critical, very simple, but if you have any problems we can discuss. So this is also solution which we obtained from the symmetry. Then we can think about energy eigenstates. So consider an energy eigenstate is like solution of time-independent Schrödinger equation, and you have a set of psi n of x, and you put these trivial phases minus I over h bar e n t, and you have this energy eigenstate solution. And with these operations, so what we require is we first need to take complex conjugation. So this is psi n star of x, and this is e to the I over h bar e n t. And in the second step, we also require t goes to minus t. So this is also a solution. Therefore, from here, right, comparing this and this, so if you have like a solution of psi n, you also have like a solution psi n star. So this comes for free. And what we see from here is time reversal, or like motion reversal, has to do with complex conjugation. So this is a purely quantum mechanical observation, right? In the classical case, we didn't have any complex numbers. In the quantum case, we have complex numbers, but these complex numbers have the conjugation which is tied to time reversal. But of course, this is still like an intuition. Now we need to define what we mean by time reversal. Now I want to introduce time reversal symmetry in quantum mechanics, right? So far we didn't decide what it is, and we need to define. Like suppose we have like initial state, and I want to use a little bit bracket notation to shorten the notation. So we have this, and if we time evolve, last time we found we have something like psi of t, which is given by u of t hitting on this psi 0. This is how we do time evolution now. We have the time evolution operator. Now I want to look at two different things. I want to compare two different ways of evolving. So what I want to do is, like, first I want to time reverse. Right? I don't know what this thing is yet. We have to find out. And this operation, I want to show it with this convention, uppercase theta, hitting on psi of 0. So I time reverse at t is equal to 0 and evolve forward. And this is going to give me exactly the same thing, u times t, an operator hitting on this initial condition. Okay. So this is one thing. And there's an alternative way, the second way. I can start psi 0, and I can evolve backwards, right? Since I have the time evolution operator, I can run it forward or backward. How do I do it? So evolve backwards by just minus t, right? U of minus t hit on here. Now I am in like t is equal to minus t, but I still need to have this, whatever this operation at this past moment should operate. And that is going to be theta times u of minus t times psi of 0. Okay. So there are two ways for me to reverse time. One is I can either reverse the time and evolve in forwards, or I can evolve backwards and reverse the time after I'm done. Okay, so it's a lot of words, but hopefully the operations are this one or this one. There is no other. And what we are trying to do, we are trying to define presence of time reversal symmetry. So if we have time reversal symmetry, 1 should be identical with 2. There should be no, if they are indistinguishable, I call it time reversal symmetric system. Good. And from there, like I use what we found last time, u of t is equal to 1 minus I over h bar h t for small t. I'm just considering only small t. Right? And I plug in, right, u of t times theta should be equal, if 1 and 2 are the same, it should be equal to theta times u of minus t. And plug this in, what I find is 1 minus I over h bar h t theta should be equal to theta, the same thing with the t goes to minus t. And it is going to be plus here. So 1 is it's just a number, right? So this h bar is also just a number. T and t are number. But for I have to be careful, right? I know, right? Time reversal symmetry has to do with complete conjugation. When I come to I need to be careful. And suppose, okay, let me write it like, don't do this. Suppose we also cancel I. Cancel I. Then what we find is minus h theta is equal to theta h. And you say like, what can go wrong? I'm just going to cancel. Let's do it and see what happens. So let's think about time-independent Schrödinger equation, right? H psi is equal to E psi. And let's do our judo move, hit with theta. So I'll just copy this and hit with theta here. So E is energy is real, so theta should jump over this. So this is theta. But here we found if you jump theta over h, you just pick up a minus sign, right? Theta jumping over here, you need to pick up a minus sign. That means we have h theta psi is equal to E theta psi. Sorry, there's like I missed minus sign here. Good. And I want to move this minus sign from here to here. And let's think about what may be wrong with this solution, right? For every positive E, there is like a negative energy, right? And there's nothing like this, right? Think about all the solutions we did, right? Particle in a box, harmonic oscillator, free particle. We never had something like this, right? There's energy is always positive, or if there's like a potential, energy is always bigger than minimum of potential. So, or another way of saying this, if this is the case, I can just have higher and higher and higher energy and hit with time reversal, and I can get lower and lower and lower energy, and I can generate a negative energy black hole, right? Nothing like this should come out. So this is nonsense. So this is nonsense. That's why I said don't do this. And from here we fix our mistake by saying, what was it? Let's do the right one. Let me cancel all of these. Okay, there's like a minus here. Cancel that. Cancel that. And I'll cancel everything. So right thing to do is when this time reversal operates on I, it turns it into minus I. So this is minus I theta h. So this is correct. Or if you want to do this, now this minus 1 and this minus 1, they can be cancelled. From here, what we find, it's h theta is equal to theta h, or h and theta commutes. Of course, this is if we have time reversal symmetry. Otherwise, we don't have that. So this is our definition. Good. Now, if we have to change the signs of complex numbers, we need to enlarge the possible operators we work with, right? Previously, we had all the operators were linear. What that means is like if you have an operator and hit something like, I don't know, f plus b g, where a and b are complex numbers, we would have af plus b bg. Af b ag. Okay. Basically, these complex numbers can just jump over operators. So these are linear. So in the case of time reversal symmetry, what we have is like this also jumps, but you need to generate a complex conjugation, right? Because of what we just observed. And this operator, what we call anti-linear. This is also a name. I don't think it's important. People just call it anti-linear. So if this operator, if we are going to talk about unitary operators, right? Unitary operators, linear. What we expect is like we have like some inner product between f and g, and under a linear unitary, or like let's call it unitary, we need to preserve inner product, f prime, g prime. So these are transformed, and this is going to be f, u dagger, u, f, right? This is under u. And from here, if we are to preserve inner product, we need to have u dagger u is equal to 1. But here, what we require, here we have fg. Under this theta goes to its complex conjugate. And what is the complex conjugate? It's gf, right? And we require this gf. So this thing, we require this to be something transformed, acting on theta minus 1, theta G transformed. And from here I require this theta minus 1, theta is equal to 1, which is correct for all invertible operators. Good. So basically, yeah. There's a little bit more than this, right? Typically, bra and ket, bra space is like a linear map, right? From the Hilbert space to complex numbers. And we have to have this linear map with some like nice properties. And if you incorporate a anti-linear operator in that linear map, you have to be careful. And you kind of hit the boundary of Dirac notation. But if you remember this, I think you are generally safe. And we will try to, like, I'll blame Griffiths here. So we'll never operate this theta on the bra space. We'll always think about this theta, whether it's inverse or not. It's always going to hit on the ket space. So that's one way of avoiding problems. Then, okay, if things transform like this, let's think what P and X as quantum operators should behave like. So X prime, okay. So this was how identity transforms. I define, okay, let me introduce. Previously we had U dagger X U, but now because we don't have U daggers anymore, I'm going to put theta to the minus 1, X theta. So what is this thing? We need to decide. And also P and P prime. And based on our classical intuition, this should go to minus P, this should go to plus X, right? This should be odd in time reversal, this should be even in time reversal. I think this one is a little bit more interesting. Let me do this and you can play with this to see it for yourself. Let's hit with P prime on like some test function f of x. This is what? This is this thing. Acting on test function f of x. Theta hitting on f is going to be complex conjugation. So this is theta minus, and P is minus I h bar del del x, f star of x. And now this theta, right? Theta and theta inverse, they just do complex conjugation, because if you do complex conjugation twice, you get identity. So this is going to be I h bar del del ex, and its hitting on f is going to be f. From here we deduce P prime is equal to, right, this is minus P. This is not vector yet. So in the general dimensions, we require this P prime is equal to theta minus 1, P, theta is equal to minus P. And similarly for x, you can do the exactly same logic, and you can find this is going to be plus. Good. And we can also check other consistencies. Like for example, let's think about the commutations. If you are thinking about xi, pj, what was this commutation relation? Does anybody remember? If you calculate the commutator of x and p, I h bar, yeah, delta ij. Now let's hit with theta inverse and theta, and similarly here, theta inverse, and from here, theta. We said x goes to x, but p goes to minus p, xi minus pj. What about the right hand side? If I do this operation, theta minus, is it like IH bar or minus IH bar, right? Because this theta minus I theta, when this theta or this theta jumps over, it's going to be minus I, theta minus 1 theta, and theta minus 1 theta is 1, so this is going to be minus I, so it is minus. And this minus compensates this, right? And we have consistency. Let's also think about angular momentum. So this angular momentum, which is L is equal to R cross P. And what do you think this should give? This theta minus L theta. So this one? So this is, can you say one more time? Above? Oh yes, so this is delta ij. Yes, thank you. Yes. What about this theta to the minus 1 L theta? What should be the right hand side? So R goes to R and P goes to minus P. So this is minus L. Or if you want, you can also think about commutation relation, Li, Lj, I, H bar, epsilon I, Jk, Lk. So L goes to minus L, L goes to minus L. There are two minuses. There is one minus here, but another minus will come from complex conjugation of I. So this also makes sense. Good. So let me, check e to the I px goes to e to the minus I px, and psi nlm will go to, let me just write the results, minus 1 to the m psi nl minus 1. And if you want to see why these are so, you can see problem 4.6 and 6.36 as an exercise. But now I want to close with one last important thing, and I'll be done with time reversal. I want to talk about spin. So S, right, the spin, which can be half integer or integer depending on the particle, is angular momentum. Therefore, we require this theta to the minus 1 S theta to be minus S, because S is like L and they should behave exactly the same. So this is needed. And let's think about spin a half, like spin 1/2. We have S written in terms of h bar over 2 sigma. Right, these are Pauli matrices. And we have three Pauli matrices, sigma x, sigma y, sigma z. And we need to find, right, a transformation which takes all of these guys and puts a minus in front of each one. We need such a transformation to be able to call it time reversal based on this expectation. And also we need complex conjugation. So I want to try an ansatz. Let's try theta is equal to subunitary operator times complex conjugation. So this is complex conjugation. So this unitary operator, 2 by 2 operator, is going to do whatever I need here. So I need to find u. And let's think about, okay, this operation also is basis dependent, and we have to be careful. Let's use standard basis. Standard basis is eigenstates of sigma z. standard basis. So it's sigma x 0, 1, 1, 0, sigma y 0, minus I, 0, and sigma z 1, 0, 0, minus 1. So what we want is like if I do the complex conjugation, right, sigma x, there's nothing complex in the standard basis, is going to go to sigma x. Sigma y is going to go to, right, there's I, minus I, this is going to go to minus sigma y. And sigma z is also real. Sigma z is going to go to sigma z. So this one is check, right? We want everyone to flip the sign, and we only did one sign flip. And we need to find a way to flip sign of this guy and sign of this guy. But this additional thing we are doing should leave this unchanged, right? We should not change sigma y anymore. We did what we need with sigma y, right? So what is the right thing to do? Maybe I can give you a picture. Suppose this is my coordinate. So this is sigma x, sigma y, sigma z. And with the complex conjugation, I have taken care of sigma y. But I want to invert sigma z and sigma y. What should I do?
Rotation.
Exactly, right? How much rotation? Exactly. If you rotate by pi around sigma y, sigma x is going to go to minus sigma x, sigma z is going to go to minus sigma z, and you are going to be done. And this is no problem because now we know rotation, right? U should be the rotation operator, and it is, if you remember, minus I over h bar, this phi dot s. But now s is h bar over 2 sigma, but we are rotating around sigma z, sigma y, so this is going to be sigma y, and angle is pi over 2. Sorry, angle is not pi over 2, angle is pi, so this is going to be e to the minus I over h bar, this is pi, this is h bar over 2, this is sigma y, and cancel this. And hopefully that's the, yes, do you have a question? No, okay. Hopefully you also look at the exercise, so we can write this as cosine minus pi over 2 times identity plus I sigma y sine minus pi over 2. If you want, you can look at another problem which I signed, like it's like 6.32, or you can look at this self-study assignment number 5 to see where this comes from. Hopefully you can do that because people may ask you about this. And what is cosine pi over 2? This is 0. And this one is, right, sine minus pi over 2 is minus 1. So this entire thing is going to be minus I times, okay, 0, minus I, 0. And if I multiply with minus I, this is going to be 1. This is going to be minus 1. Therefore, for spin a half, our time reversal operator is 0, minus 1, 1, 0 times complex conjugation. Okay, I need to take 5 more minutes for my computer malfunction because we need to finish this story. I think this is the most interesting part. Any questions? So now let's see what this time reversal operator does to spinners. Let's consider it like a spinner. I don't know, let's say chi AB, and I want to hit on this theta times chi is equal to 0, minus 1, 1, 0, k times a and b. And a and b are complex numbers. And this is going to give us, right? So this is 0, minus 1, 1, 0. Complex number is going to give me a star and b star. And now if I do the matrix multiplication, this is going to be minus b star and a star. Good. So this is one time reversal. Let's do the time reversal one more time. So theta squared chi is equal to, again, this 0, minus 1, 1, 0, k times this thing. And this is going to be 0, minus 1, 1, 0 times complex conjugation is minus b star of star is b, a star of star is a. And if I do the multiplication, what I find is minus a minus b, which is minus chi. Right? So if I do the time reversal twice on a spin and a half, I don't get back to state, I get back to minus 1 the state. Right? And you should also compare this 2 pi rotation of spin and a half. This is unusual, but we have to live with this, right? And there's like consequences of this. Any questions? Let me show you one consequence of this, and then I'll close it there. So we are given this theta square is equal to minus 1 for spin and a half. And suppose I have like a time reversal spin and 1/2 system. And what does it mean? I have h and theta 0, right? That's what we introduced earlier. And let's write time-independent Schrödinger equation. H psi n is equal to En psi n. And we do our judo move, hit this with theta from both sides, but E is real, so it's going to be like here. But they commute, right? If they commute, I can just move H as I want. And from here, what I found is almost like the same story, right? If psi n is a solution, theta times psi n is also a solution. But the next step is, are these two solutions are the same or different? Because if they are the same, there's no degeneracy. But if they are different, that means I have a degeneracy due to this symmetry. Suppose they are not the same. For like I'm from here on, I consider only spin and a half system. Suppose they are the same. That means theta times psi n has to be some coefficient c times psi n. Then there is no degeneracy if that's the case. But what I can do is I can hit on this with theta one more time. Right? This is theta squared. And now here I have to be careful, right? This is theta. And this c is a complex number. And we know how c or what theta does to c. It can jump over it, but it's going to be complex conjugated. Now this thing, right? I can use this one more time, right? Theta times psi n is c times psi n. And from here I found c squared psi n. But above we said theta square is 1, theta square is minus 1, right, here. So this is minus 1, and this gives us c squared is equal to minus 1. What does it mean? Huh? Exactly, this is nonsense. That means theta psi n and psi n are distinct. but same energy. Okay, so there's like an inherent degeneracy due to symmetry, like we argued before, but this is specific to spin and half system, or like half integer as a matter of fact. And there's a name for this. This is called Kramers degeneracy. Or this thing is called Kramers theorem sometimes, or theorem. Good? Yes?
John, in previous lectures, we found like extra degeneracies, like are they related? This is
Of course, it's related, right? If we have a symmetry, it's like a tricky thing. If you have symmetry, there's like a commutation, right? And then what is the condition for us to have degeneracy? And in the case of this time reversal symmetry, which is like a discrete symmetry, we have a degeneracy which was unlike what we had before. So this is a completely different in its structure. But the general theme is still the same. There's like a symmetry, and because of symmetry, there's not always the case, but for this case, there's like a degeneracy. And this one, for example, doesn't exist. If we had integer spin system, theta square would not be -1, right? Theta square is not -1, and for integer spin, that would not imply a degeneracy. Only for half integers. Good. Any questions? So this is a little bit tricky. Don't be scared too much. But I think people will tell you about time reversal symmetry, and my experience, nobody ever teaches what it is. And textbooks are, I think, a little bit not good enough. Like Griffiths, for some reason, thinks it's not important enough to make a section. But I think it's very important. And if you don't get everything now, it's fine. Don't be scared. But in the future, you can refer back. Okay?